right, we can go ahead and get started. We'll get the people out in the coffee area in here, and I have to get my, you'd think I would know Wojtek enough not to have notes to introduce him, but I still have my notes right here. So Dr. Wojtek Grabowski is a senior scientist in the Dynamical and Physical Meteorology section of MMM. He received his PhD in 1987 from the Institute of Geophysics in Warsaw, Poland. He came to NCAR in 1987 as an ASP postdoctoral fellow. He is a fellow of the American Meteorological and Royal Meteorological Societies and is the recipient of several awards, including being named as a titular professor of physical sciences of the Republic of Poland, which I'm not exactly sure what that is. Maybe Wojtek can explain that, but.
Well, one thing that is nice is you go and shake your hand with the president of Poland. because this is the title. It's not a position like in US universities, it's the title. So there's not that many people. But anyway, so there's.
Okay, well, you heard it directly. So Wojtek's work spans a range of topics related to geophysical fluid dynamics, turbulence, and cloud physics, which he will cover today. And you're going the long way around, I guess. Okay. Over to Wojtek.
Thanks for coming. This will be kind of a trip backwards in time. You will meet some people that some of you never heard of. Some of you knew quite well. So it's a kind of a, for me, going back when I started here almost, as you will see. So let me give you a plan of this road trip. Will be a little bit of motivation. We will talk about two papers that some people of my age knew in person, I hope. There will be some ideas that go out of those papers, went out of those papers, and we will kind of cover some initial research. When computational resources increase, we try to make kind of bigger simulations, if you like. And of course, fairly recently, we realized, and that's why, by the way, Gustavo Abade, my colleague from Warsaw, is co-author, because he had brought me to the idea that we've been doing it completely wrong. And you will see what I mean by that. And some ideas how we can actually move forward. So why we worry about droplet spectral width? Just a couple of simple examples, obvious to most of you, I would imagine. The effective radius, which is used in studies of radiative transfers to cloud, especially solar radiation, because that's when it really matters, is a ratio between third and second moment of the droplet size distribution. And of course, for monodisperse, the effective radius would be just equal to the radius, because there's only one radius. But if you get a distribution, these two are different. And the effective radius changes if the droplets are broader than the difference between effective radius and mean volume radius, because this is something like that, it gets larger and larger. And of course, gravitational droplet collisions will not happen unless you have droplet spectral width size distribution, because if for the monodisperse, there will be basically no collisions unless there are some other effects, like turbulence, for example. So going really back in time, why we worry? Of course, observations, this is where our knowledge comes from. So if you look at the paper that Jon Jensen wrote in mid-80s, I think that was his dissertation, looking at clouds, not like those clouds over the ocean, but actually looking at clouds in CCOP in Montana in early 80s. There was a big project. I think some people in this room were involved. Charles, were you involved in CCOP? I think you were, yes, indeed. I was just a graduate student there, so I wasn't. The point here is that if you look at those spectra, those are observed spectra using technology then, 100 meter, 1 hertz data, so about 100 meters of the flight path. You can see that the spectral, which is relatively large in those examples, especially comparing to adiabatic spectrum that you calculate, which is very narrow. 1/10 of a micron, look at the logarithmic scale. I mean, it doesn't look like 1.5 or 1 micron, but that's a logarithmic scale. So the spectrum always looks broad, but if you plot it in a linear scale, then it really shows that it's relatively not as wide as here. So moving roughly 20 years, another example, more recent, the paper that we wrote with my colleague from University of Warsaw and Jean-Louis Branguier, that some of you know him, now retired from French CNRM, meteorology at the end, showing the observations in stratocumulus, so something like that. We're looking here only at kind of close to adiabatic droplet concentration, mean radius, and spectral width. And again, those are two different, these are kind of relatively clean, those are more polluted. And again, spectral width is maybe 1 to micron. So that's something that we would like to understand, especially with this argument that if you take a parcel, adiabatic parcel, nothing, no entrainment, of course, because you would like to have adiabatic, but also no other processes that may contribute to having wider spectra. You may ask where this comes from. So I told you that I will bring two significant papers. One is from Al Cooper, that most of you know the name and know the person, basically arguing that if you look at the droplet spectrum in one place, in a cloud, this spectrum comes from droplet trajectories that come basically from different parts of the cloud and are united, if you like, in one place. So that's what we coined the term with my colleague, Yanping Wang. You know him. He was affiliated scientist in our division a few years back. Now he's in China. They basically bought him back, if you like. The argument is that those different trajectories give you spectral width. And the example of those different trajectories comes, for example, from simulations that Kamal Chandrakar, we will talk about those, did. So those are trajectories, if you like, arriving at different points, and you can see how different those droplet trajectories are. This is a special approach that I will bring later in my presentation. It's we call it super droplet method. That's the Lagrangian approach. It's not mixing ratios as we do typically in cloud modeling. That's a novel approach that we are using. And you can think for the moment that these are those droplet trajectories. And they end up in different places in the cloud. So this is what you may think of like eddy hopping, that basically turbulent cloud, those droplets hop those eddies and end up eventually in one place, and then you can look at the spectrum of those droplets. So that's one paper. That's those trajectories. There's another paper that I would like to bring in. Ramesh Srivastava, exactly the same year, 89, published a paper arguing that we have things wrong in cloud physics because we kind of tend to think about relatively large volumes inside cloud that rises, and droplets are exposed to the same conditions. So Srivastava was arguing that this macroscopic approach, that basically you have a volume of a cloud, you have droplets, and you apply mean temperature, mean water vapor to those droplets is wrong. It's not appropriate because in reality, we know what happens. Droplets grow by the diffusion of water vapor and temperature. When the parcel rises, the air gets cooled by adiabatic expansion. So we need to think about microscopic approach. In other words, thinking that each droplet may grow in its different environment, not mean environment, not macroscopic environment, but just in the microscopic approach. So basically, that was late 80s, early 90s, and then I got the idea, well, maybe the small-scale turbulence can explain the width of droplet spectrum in undiluted cloudy volumes. In other words, imagine the volume that is not being diluted, just rises, but it's turbulent. Can this explain spectral broadening? Now, if we use direct numerical simulation, that's a computational approach that I will explain in a moment, then indeed, you may think that individual droplets follow different trajectories through a turbulent cloudy volume. So here's Al Cooper argument. And of course, each droplet will grow in conditions of its immediate environment. So this is the picture that you can kind of have in mind. So this is grid box of DNS simulation. This is kind of the example of what we're doing. This about 1 millimeter, because that's the Kolmogorov scale. So the grid length has to be like a Kolmogorov scale. Droplets here are not to scale. In fact, the droplet, 10 micron droplet, would be a small, tiny dot, smaller than my pointer here. But the positions are kind of like what you would imagine. With typical 100 to 1,000 droplets per cubic centimeters, you would have 1, maybe 2, maybe 0 droplets per grid volume. So this droplet will grow in each volume. So that kind of makes sense to try something like that. Okay, another person that some of you may know, we used to have a DNS person here in this division. I will not use the name. Some of you would know who I'm talking about. I approached this person and asked him, can we do it? He said, well, you know, I have a bigger fish to fry. I'm not worried about droplets in some kind of clouds. I'm a turbulence person. So I said, okay, okay. So what I did, I contacted my good friend and colleague, Peter Yao. You may know Rogers and Yao textbook, very simple cloud physics textbook, so that's my colleague. And also there was a turbulence at McGill, turbulence person, Peter Bortello. So I approached them, and they took Paul Vollencourt as a PhD student. We worked with Paul before on a master project, and we look into this. So basically, Paul took a code from Peter Bortello, and with help did the research, basically looking at droplets in a turbulent flow. That subject was actually quite of interest to turbulence people because of the effect turbulence has on droplet positions. I mean, those are heavy particles, remember it, about 1,000 times heavier than air, so they slowly fall, but at the same time they respond to the turbulent flow. And this picture is supposed to show that. So on the left panel, it's a vorticity into the plane, and in those panels are position of small droplets in this flow. So the flow is the same for all of them, starting from larger here, 20 microns radius, 15, 10. And what you can clearly see is that the larger droplets have a little bit more unrandom, not random positioning. That's because of inertia. So a lot of people were worried about that. And of course, we wanted to look whether that has any effect on droplet sizes. Now, here, the interesting aspect or relevant aspect is that this is really small domain. This is just basically a box like that, 1 liter, 10 by 10 by 10 centimeters. Nevertheless, starting with completely uniform distribution after some time, as you can see, this time is relatively short. Well, think about computers in the early or mid-90s. But there is something interesting here because it shows result of simulations, how the spectral width increases with time with different processes eliminated from the simulation. So for example, when droplets have no inertia, then of course they would not respond to those flow structures. And perhaps should say this is fairly well understood now. I mean, think about this as those are eddies. So they basically expel those heavy droplets outside, like a centrifugal force. So that's why you have holes here, and bigger holes or more holes when you get larger droplets. This is factor of 8 in terms of inertia, 2 in terms of radius. So these droplets are expelled. And of course, if you take this away, if there is no droplet inertia, droplets will basically be more randomly distributed. So this standard deviation evolves slower. If there is no sedimentation, it's actually the highest. Why it is so? Well, because those droplets fall quite quickly. This is just 10 centimeters. 10 micron droplet falls about a centimeter a second. So it will fall through those structures. If you eliminate this process, then of course it will the radius will increase, standard deviation of the radius will increase faster. Okay, so that was, this was published in 2000, but actually most of the work was done a few years earlier than that. So now the question is, are you worried that this box is relatively small, and why the domain size, the box, matters? And the other question, if it does, how we can make DNS with bigger domain. Okay, so next few slides will address that. This is fairly complicated, but imagine, so this is your DNS box with size L, and this just shows that there is something going on there. Rich?
So if you take away everything, why should the droplet spectrum broaden at all?
Well, because each droplet still responds to the local environment, which is changing rapidly, but still it's not the same for every droplet.
Oh, okay.
So there is molecular diffusion at that scale. So all of that produces some increase, but it's very, very slow, obviously. Okay. So I would argue we need a larger domain. That's basically the point that I will make. So why you want to have larger domain? Well, because if there are no droplets and you just have turbulence with box L, then the supersaturation standard deviation in this box will really depend on the size of the box. Why it is so? Because the equations that you solve, the water vapor is a scalar. Imagine there's no droplets yet. It's just to show why domain matters. And the temperature is scalar, except there is a source that is related to vertical velocity. That's your simple parcel expansion when it rises on a very small scale here. Now, and that term is proportional to vertical velocity. So it's really, so the temperature change will depend on how far the small parcel inside the simulation goes. Okay, that's why the domain size matters. If it goes a little, the temperature changes a little. If it goes more, the temperature will change more. So that's why parcel size is responsible for the supersaturation fluctuations. Now, TKE doesn't matter. TKE is turbulent kinetic energy. In other words, whether you go up fast or you go slow doesn't matter, because it's just how far you go. Okay, there are no droplets yet. Imagine, droplets will make things a little bit more complicated. But also the Reynolds number doesn't matter. This is, for this one grid, I ran two simulations, 64 cube and 128 cube. It also doesn't matter. Why? Because it's really not a small scale. It's just the large scale that matters. How far you go, that matters. So for you turbulence people, let me bring this slide saying that, you know, typically in turbulence simulations, often the key is the Reynolds number. Reynolds number in this kind of a case is the ratio between the box size or the large energy-containing eddies and the Kolmogorov dissipation scale. And it's actually related to Reynolds number with this relationship. In our case, that's really not what is important. It's really not the Reynolds number. It's just basically how big is your box that you're doing your calculations. So that's why you would like to have as big box as possible. And in fact, a few years later, Alessandra Lanotte, that's, if you look at the names here, those are alphabetical. So I'm unhappy with physics community because they put their names in alphabetical order. My daughter, who is theoretical physicist, does the same thing. So if you are A, you are good. If you are Z, you are not good. And this is basically work that Agnese Seminara, who is now professor at one of the Italian universities, did with Alessandra and Federico. You may know these people from turbulence work. Anyway, the point is, they did a series of simulations, basically making the domain larger and larger, of course, more droplets to follow, so on and so forth. And they come up basically with this picture that if you change the Reynolds number, then the standard deviation, now we're looking at standard deviation of radius squared, and we will be looking at that, continue looking at this specific parameter, because if there is, for the droplet growth equation, this is the droplet growth equation. So supersaturation fluctuations will affect the perturbations of droplet area, if you like, so R squared. Anyway, the point is, the larger the domain, I marked here the domain sizes, the larger the domain, the larger the R squared, okay? And in fact, in the paper that I was very happy to review it because they were arguing in that paper, in the version that you will not find in JAS because that was before it was published, they were arguing, if you would extend this to Reynolds number in clouds, you will have huge spectral width, which of course is not the case because if you go to larger and larger domains, supersaturation will saturate because you will have what we call a quasi-equilibrium supersaturation. So if you go to larger domains that, you know, half a meter here, that the physics will change. I will not talk about that, but anyway, they took this, and this paper doesn't claim that if you go to big domains, big Reynolds numbers, you will get huge effect. Anyway, so let's move forward in time. Physicists got interested in the problem, and they actually developed a theory, basically, that says, and I will not show you the whole derivation, I will explain basically how they get to this theory, if you like. And that basically, if you start with this box and you run it long enough, here, this from Alessandra, was basically after one edit and over time. So there was basically just snapshot. It's not evolution in time. Here we're looking at the evolution of time, and they claim that the standard deviation of radius squared should increase as a square root of time. So how they got into this? First of all, this is the equation that if you do perturbation thing, the radius square standard deviation squared depends on the correlations between supersaturation and radius squared. There is some math involved, but their theory applies to the situation that phase relaxation time is much larger than turbulence timescale, if you like, much smaller than the turbulence timescale. So in other words, it applies to relatively large eddies because this phase relaxation time is about 1 second. I like showing this figure from Politovich and Cooper paper, which shows those phase relaxation times for specific thermodynamic conditions as a function of droplet concentration and droplet radius. Now, you can see that it varies from, let's say, several seconds to fraction of a second, but the point is, we know from cloud physics that when you get low droplet concentration, you typically have larger droplets. If you have high droplet concentration, you have smaller droplets. So the kind of cloud physics relevant numbers are on the diagonal. That's why I'm saying that the time scale, the phase relaxation time scale, in other words, how quickly the droplets respond, removing supersaturation fluctuations, is really about 1 second. So this theory really applies to relatively large eddies because to have a turbulence with a time scale of, let's say, few seconds, several seconds, requires these eddies cannot be very small. And then they actually derive, using those assumptions that derive that this standard deviation of radius squared should increase as a square root of time. So this is from their paper. Those are simulations that they've done. And they basically show that indeed, this is square root of time, that the standard deviation of radius squared evolves pretty much like square root of time. And here they're basically showing how this correlation looks like. Of course, fluctuates a lot, but if you average it, it's basically constant. Now, when I look at this result, what struck me is that the theory really applies only when the time scale is much smaller than the phase relaxation time scale is much smaller than the time scale of turbulence. And if you look at those two numbers here, I think I marked it not correctly. This is the turbulence time scale. And okay, if this is about 1 second, see that this is not much smaller than that. It's the opposite, actually. But nevertheless, they got the scaling from the data. So how is that possible? We will answer that later, which explains what's going on in those simulations. Now, so let me switch gears a little bit and show you something that we've done with Lois Thomas. You may remember her. She visited ENCA a couple times. She finished her PhD a year and a half ago. So the argument here is that the DNS domains are small, and it's hopeless to expect that the computers become large enough to run, let's say, 100-meter cube or 20-meter cube domain with LES. But we would like to run those simulations with big domains because the turbulent kinetic energy depends on the domain size. And of course, when you get supersaturation equation, that's the supersaturation equations that we are solving. If you get large domain and you get large velocity perturbations, so this driving term is large, then you expect, and also you have longer lasting supersaturation perturbations. So we would like to go into larger and larger domain. How we can do it? So in other words, the question is, can we extend traditional DNS simulation methodology that is applying a spectral code with triplet periodic boundary conditions? This is kind of the tool that we're using into larger computational domains. So we came up with Lois, and Bipin, you may remember Lois when she visited here. I remember we talked with Peter. Peter should remember her. How to do it. So we came up with the following idea. So if you think about cloud turbulence, so this is where energy is put through the eddies, and it's dissipated at the Kolmogorov scale, and you get inertial range, which the kind of a spectral code can represent what happens here. And of course, you will have to have dissipation at 1 millimeter. If you would like to cover all the spectrum, that's 5 orders of magnitude, so it would be like 100,000 cube grid. I don't think even the youngest people in this room will see it in their lifetime. Definitely, I will not see it. So what we can do? Well, DNS does the following thing. It keeps this dissipation scale at 1 millimeter and tries to get this energy containing scale as far as possible. At the moment, it's maybe a couple of meters, maybe 10 meters. And this is the range of scales that models simulate. But what if we do something like that? And remember, the idea is that we know that larger scales are important. So we would like this part to be large. We don't care so much about dissipation scales. So what if we would change the viscosity of the flow and transport coefficients, that the Kolmogorov scale is no longer 1 millimeter, but for example, here in this example will be 10 centimeters. And then we do the same simulations like here in this range, but we will do it in this range. So that's indeed what we did. So the idea, if you do the math, this is how you need to scale up your transport coefficients depending on the domain size. So this will be your DNS, this will be your scale-up DNS. And I'm showing here the energy of the spectral energy, if you like, or energy density, I think, in fact, what it is. Starting with real DNS, so this is 256 cube over 25.6 centimeter domain, and then you go to domain 2.5, 25, and 256, and you can see if the energy gets larger, because that's kind of natural, but it kind of holds up pretty nicely, okay? So now we have a tool that we can do large domain, okay? Now we have to do something about droplets, because if you have a grid box which is 10 meters or 1 meter, you will have billions of droplets in it. So you cannot follow all of them. So what we're using? We're using a super droplet method, which is a technique that invented and I think patented by Shima, our Japanese colleague, with the idea that rather than looking at the cloud of droplets that looks like that, this is just the illustration of the idea. When you get droplet size and cloud condensation nucleus size, you basically have computational particles which have multiplicity parameters. So in other words, it tells you how many droplets it represents. So if you are in the middle here, the multiplicity is high. This is where it is. And if you are on the edges, the multiplicity is low. So you can use this approach to represent billions and billions of droplets with something which is computationally manageable. So we've done that. And this is example of results that Lois got. Again, square root of time scaling, and the different domains, 2.5 meters to 64 meters. You can see that the scaling still holds up. And of course, the higher you go, the larger the standard deviation is. And this is just the illustration of what happens. You start with very narrow droplet, and eventually they spread out because of those turbulent fluctuations. Okay, so we covered one technique that you can use. Now, there is another approach that you can use into this problem, which is a stochastic model. So the stochastic model for droplets growth, in this case by condensation, if you think about this box filled with turbulence, you can come up with a relatively simple model to describe that, that basically droplets grow because of supersaturation fluctuations. So the R squared perturbation goes with the supersaturation fluctuations. The supersaturation fluctuations, that's the equation that I already showed you. So this is droplet growth equation. So that's kind of like condensation rate, if you like. And here you get the forcing through velocity perturbation. And that's the key, because this forcing comes from Langevin equation, which is a stochastic differential equation that describes perturbations in a, let's say, turbulent flow. And then the solution of this equation, you can march in time, if you like. So next time level, dt would be your time step, comes from basically remembering what was the previous time step and some random forcing that comes from the velocity perturbations, if you like, that you drone randomly. So that's, in turbulence, that's a fairly common approach, and Gustavo exposed me to this methodology, which me being cloud physicist, I was not familiar with it, but actually it's simple and it's very efficient. How you apply it, basically, so these equations are for just one droplet. So you just follow basically thousands and thousands of droplets. You can run it on your laptop very quick, and you basically get the same result, which we actually showed in this paper with Lois as turbulence. Now, so we use this approach with Gustavo to look at a little bit more complicated, but perhaps more relevant to cloud physics problem, that you get the parcel that rises, it activates cloud droplets, and droplets glow by diffusion of water vapor. And the idea in this paper, published maybe 5 years ago, 6 years ago, 7 years ago, to compare traditional adiabatic parcel, when there is no turbulence, with a parcel that is filled with turbulence. And turbulence is modeled with this relatively simple stochastic model. So the adiabatic parcel, this is something that many of you are familiar with 1 meter a second updraft. So this is height, actually perhaps should be in a vertical, time in seconds, or height in meters, if you like. And it's fairly familiar. Your supersaturation increases. That's why you activate droplets. Then it kind of levels off. Mean radius, there is something during activation, which is not so important. Then radius increases, and the spectral width decreases. So there is nothing fancy about it. And of course, there is more and more water, because that's the cloud water, basically. Now, if you do the same thing, but now you get a parcel filled with turbulence with some prescribed dissipation rate, because these are two parameters that basically decide your solution. The only difference with the previous plot is that I'm also showing the standard deviation of the supersaturation. To show these two side by side, you can see this is spectral width and there are no turbulence, the adiabatic parcel. This is parcel with turbulence. And you can see that adiabatic width is here much higher than before. So we were, of course, very happy, because if you look at the spectra at the end, when there is no turbulence, the spectral width is small, a few tenths of a micron. But if you have turbulence, it's something which we've seen before, about 1 micron. So we were very happy about that, and of course we published a paper and this and that. And then we start thinking, is there something that we're missing in all those approaches that I showed you? And in fact, it is. And that brings the basically fundamental flaw, if you like, in all those stuff that we've done over the years. I'm sorry, but I don't feel uniquely responsible for this. Where is the problem? Well, if you think about this periodic box and droplets, if droplets leave through the upper boundary, they come from the bottom. That's basically your triplet periodic domain setup. There's no way around it, at least in this kind of the way we pose it. Whereas if you think what happens in nature, the droplets will basically keep going up. They will not come back from the bottom. And why that is important? Well, because if you have two droplets, one is going up, one is going down, and you look at those equations, so temperature and moisture, now we have condensation, so that's growth. That's the supersaturation equation. So these two, when you combine, you can solve for temperature and water vapor. You can solve for the supersaturation, whatever you want to do. And that's the quasi-equilibrium supersaturation if you get large eddies. But the point is the droplets that go up become larger. Droplets that go down become smaller. So if you have periodic domain, this is what happens, not surprisingly. Large droplets, before it leaves the domain, boom, it comes from the bottom, goes to the bottom. Smaller droplets that end up leaving the domain from the bottom comes from the top. Okay, that's a problem. So maybe what we've been doing is actually not right. If you think about the stochastic model that we've done with Gustavo, so we basically calculate droplet growth through these perturbations of the mean growth, we haven't considered where the droplets end up. So let's redo those simulations. And now, in addition to droplet perturbations, you look where droplets end up being when they finish after some prescribed time. This is what happens. If you count all the droplets, and this is for specific simulation, if you count all the droplets, there you go. You recover the square root of time scaling. But if you limit yourself only to droplets that remain in this range of heights, after some initial time, then basically saturate. There is no longer the effect. And there is some noise here because, of course, there is less and less droplets inside this area, this height range to consider. They basically move. Okay, if you do those simulations with different domains, well, basically the same story. You shouldn't expect any difference. So this is different dissipation rate. This is very high. This is relatively low. So this is like extreme, cumulus cloud summer inside, very turbulent. This is kind of like stratocumulus, nothing special. But the same picture, 1 meter, 10 meters, 100 meters, basically the same story. That this is the scaling that the theoretical physicists derived, but in fact, droplets that remain in this range are there. So that actually explains why, in this continuous growth, why they had this scaling, despite the fact that the 1 second time phase relaxation time, roughly, is not much smaller. So you may ask, okay, so what's going on? Where the scaling comes from? So where does this scaling comes from? Well, we have to move back 120 years. We have to move back to Einstein because this is simple scaling that Einstein derived in 905, considering Brownian motion. So the random walk model gives you spread of particles, basically exactly like that, with the standard deviation of position of particle in random walk given by times a square root of time, okay? And so, okay, so how I can prove that this is really happening? Well, in those simulations that I showed you, let's look at sigma z, so standard deviation of droplet positions. Okay, all those simulations that I showed you here, here, let's take all those droplets and look how the standard deviation of position changes in time. And that's exactly what it is. So if you get large domain, large perturbations of transport, if you like, you end up spreading them more, but the standard deviation follows this square root of time scaling. So this scaling is really not about droplet growth, but it's about droplet spreading. In other words, if droplet is higher, it will be larger. If droplet is lower, it will be smaller. So that's basically what it is. Of course, that's disappointing because something that we were trying to catch is actually not a catch at all. So the question is, where we go from here? What we can do to actually quantify this effect better? So what about if we do not a turbulence simulations in a box, but we do a cloud simulation with high resolution. So let's say grid length maybe 10 meters. This is what we can afford today. And we use the Lagrangian particle-based microphysics. So this is the super droplet method. So it's not super droplet in a box, but now for entire cloud. And it's doable. And we can include turbulence effects. If resolution is high, you will resolve turbulence, if you like. But also, the subgrid scale turbulence can be done through stochastic modeling, exactly similar to what I showed you in this turbulent parsing. So Kamal is really leading this effort, doing those simulations. And I will show you some results, very preliminary, because I just put my hands on the data, actually, within the last few days. So we had this ASD, which stands for Advanced Scientific Discovery. That's what it is, the acronym, that Kamal ran. Basically 12 by 12 by 11 kilometer domain. Grid spacing is 7.5 meters. Superparticles, you get 64 by this box, but I will average into 5 by 5 by 5. So this would be like 30 some meters, close to 40 meters. And down there is some cloud physicists. This is fairly polluted environment. This is how cut through the cloud looks like. Okay, this is just mean radius. If you would do spectral width, basically the same snapshot, but now we're looking at spectral width. And to look at the adiabatic part, we will be looking just at the bottom, a little bit near the bottom of the cloud. Because, of course, here, it's no longer adiabatic. We see that cloud water increases, but of course, now you have entrainment mixing. It really gets complicated. So let's look at this cloud. So what I did, I basically pick up this kilometer by kilometer area, and at each height, I did average. And again, this is, as I said, 5 cube. So 5 by 5 by 5, and this is the spectral width. And you can see it kind of changes, varies a lot. Cloud base is somewhere here, between few tenths of a micron to maybe a couple microns. Actually, I truncated the plot. There are some points which go even further. If you basically imagine that you have an aircraft that flies through it, so the radius is about 9, 10 microns. It increases a little bit because there is a little bit of shear here. So probably the updraft varies. The spectral width varies between few tenths of a micron to 1 micron. Now, this is something that, of course, aircraft cannot do. I can fly my imaginary aircraft basically straight up and look what's going on. And this is what it is. So I have basically two. I promise you this is randomly selected, basically shots up, if you like, a rocket that flies and measures droplet size and spectral width. As you can see, depending where you are, the cloud base is somewhere here. So this is the mean radius, which is small. There are still some Deliquest CCN in this simulation, and then droplets begin to grow. And as you can see, spectral width, this is just random. It's either small or a little bit large. So there is a lot of data to dig through and understand what's going on in terms of activation. So I think this is the approach that will perhaps bring everything together to understand where the spectral broadening comes from. One thing that can be easily done is to take this aerosol and run adiabatic parser, which I haven't done. But I expect that this will be a little bit, or maybe quite a bit narrower than this. Of course, this width comes from activation. I also did simulations with activation and show how turbulence affects activation itself. Okay, so this is the conclusion. A lot of words. Basically, the understanding the droplet spectral broadening due to diffusional growth in turbulent environments attracted significant attention of turbulence community in recent decades. DNS, scaled-up DNS, and stochastic models have been used to show the impact of turbulence in undiluted cloudy volumes on the adiabatic droplet spectral width. And in fact, there were some DNS studies that also look at the effects of dilution, which you can basically put into forcing, adding special terms for temperature and moisture sources of variance, if you like. So there was a study that did that. Theoretical analysis suggests that the droplet area, so radius squared, standard deviation should continuously increase in time with the t square root of time scaling. This has been confirmed in several investigations of droplet population growths in isotropic homogeneous turbulence. It follows that the droplet spectra and undiluted volume should continuously broaden above the cloud base as the updraft carries droplets upward. And in fact, if you look here, I'm not sure whether we actually see that. So that's kind of like a warning sign, if you like. However, those idealized studies feature a fundamental flaw of periodic domains that allow droplets to circulate in the vertical. If droplets' vertical spread is taken into account, the spectral width saturates. So that's basically that I showed in this simulation. So this is when you count all the droplets. This is when you actually look only at those droplets that remain in your initial domain. Where is that? Yes. So this square root of time scaling comes from the droplet position standard deviation as in the random walk model. And that basically goes back to Einstein, but also other people who work on Brownian diffusion and things like that. And finally, analysis of realistic high-resolution cloud simulation. We need to have high resolution, really. Some may argue even 10 meters is not good enough. Applying Lagrangian particle-based microphysics will help further quantify the impact of turbulence resolved in subgrid scale. And I think subgrid scale here is quite an important point, because the approaches that we've been using for cloud modeling in the past really don't have a robust subgrid scale modeling for droplet growth. And this approach with Lagrangian microphysics has great benefits. And of course, if you think about collision coalescence, that's kind of completely different kind of worms that I didn't talk here. But Lagrangian microphysics is also great of that, because it includes elements that we believe are important for rain formation and also for ice as well. So I will stop here. Thank you for listening for my, how to say it, not so great story in terms of the final outcome, but I hope you enjoyed the ride. Thank you very much.
All right. Questions?
Thanks, Victor. It's a very nice talk. Just one comment about this eddy hopping mechanism. Like you mentioned, like of course, like vertical transport can like make the spectrum with broadening saturated with time. And yes, yeah, that's expected because there's time scale limitation because of the transport. But then that assumes like supersaturation fluctuation is mainly driven by vertical velocity, not accounting for fluctuation in the water vapor. So if there's any decorrelation between temperature and water vapor because of the other processes like water vapor fluctuation through entrainment or like variability in the cloud base, like etc., that could kind of change the result a bit. Like you
well,
get
probably quite a bit, I would say.
Yeah.
Here we're looking at really and I mean the reason why we're looking at the adiabatic part, because we understand from some studies that the collision coalescence really begins in those practically undiluted volumes, because that's where the liquid water is the highest. And some of you may remember this famous quote from, I don't remember who was that, saying that because people were looking at the entrainment mixing effect on the collision coalescence, and the argument was that looking at the dilution accelerating rain formation is kind of like trying to boil water faster but turning down the gas. Because entrainment, of course, reduces liquid water, and you would like to have the highest liquid water possible. So yes, that's why we're looking at these adiabatic volumes. And that's why entrainment, something that we've been looking from your simulations for quite a while, I would imagine, because that's a fantastic data set that we can dig into. And maybe restart some simulations to look at some short intervals of what happens at cloud edges, for example. There's a lot of stuff that you can do with this data.
I'm not sure if you have that plot, Wojtek, but of the spectral width in that CAMP2X simulation, but you can clearly see, so on the up shear edge there, you can see that the effects of entrainment are really dominating, right? Because you go from something that's like around 1, like you said, in terms of the sigma r, up to something that's 3 or 4 times that, right along in that really sharp boundary.
Yeah, and there is a little bit of shear here, so that brings some arguments that Telford had with some of their papers, and I'm pretty sure that this kind of a downshift side is more diluted, and here is the air is trying to make it, but not quite, because you get entrainment here. So this will be definitely something of interest to look into.
All right, we'll go to one of the questions online from Annie Heimsfield. You show data from CAMP2X observations in tropical convective clouds generally indicate that the updrafts are non-adiabatic, indicating that there's significant entrainment, which can obviously affect the drop size distribution. How is this handled in your drop size calculations? So covers a little bit what we just talked about, but.
Well, so this is simulation, not observation, obviously. So whatever model predicts locally, then you take those droplets to calculate the spectral width. I'm not sure if this is what Andy was asking. Maybe I should read what the question is. I didn't show anything from observations. This is model simulation that is based on, and I would love to see observations that would give you a picture like that. I mean, sorry. That doesn't exist. The radar is probably the best, but still not at 7.5 meters. It's maybe 50 or 100 meters. So we are far away observationally. So we still rely on either satellite data, which is skewed view, or aircraft flying 100 meters a second. Maybe with drones you can do a kind of cloud-based ascent, something like that. There is a question in the back here.
Yeah, since you mentioned radar, I'm actually a radar scientist from EOL, and I work with our cloud radars, and I was actually very much reminded of what I'm seeing with our cloud radar, with this image that you're showing here. And our radar resolution is 20 meters, so maybe we should get together and look at that.
Sure, absolutely.
Okay, let's go to maybe TrueIndex, since it's nearby.
So what is your opinion of using DNS now in the future studies?
Well, be careful with it. In other words, we know what to do. And I have simulation that I didn't show. Basically, I thought that it's easier to show it with my stochastic model. If you know the droplet is leaving the domain from the top and needs to come back from the bottom, you cannot assume that the size is the same, because that skews the distribution. You may say it kind of comes back as a mean, or if you know...
Can you use the mic?
Oh, I'm sorry. If you know that there is a gradient of radius with height, then if you take a droplet from the top, or particle, doesn't have to be droplet, maybe ice particle, you should bring it back at the size that you expect it to come from the bottom. So, it's a very good tool, but it has some limitations and in fact, it's so funny, because when Paul Vollencourt was defending his PhD, And one of the reviewers asked, what about these periodic boundary conditions? And we didn't pay attention. And in fact, Lois, one of the Indian reviewers, because of course she defended in Indian Institute for Tropical Meteorology, had the same question. And that actually what got me thinking. We were already thinking with Gustavo that there was some fundamental problem. And I didn't tell her. I didn't want to stress her because, I would imagine, having a PhD defense is kind of stressful. So let's leave it. Let's her handle it. So she defended. So apparently she did it okay. George has a question.
I should have perhaps multi-part question. So I'm trying to tie the two parts of your talk together. This is LES. And so why do we even need DNS? You can do really high Reynolds number LES now, which is what Kamal and company have done. So
yes.
Why not? Why keep doing DNS?
Well, because at the time when we started with Paul, the cloud models were running like 200 meters. So and the question was whether the turbulence, going back to Cooper, going back to Srivastava, looking at individual droplets, the DNS seems like a natural tool to do it. Of course, here, it's not only LES is not enough. If you would do LES with whatever bin microphysics, you will not know those different trajectories that super droplets take through a cloud. So we basically had to wait, 20, 30 years to get technology that allow those kind of simulations. And it's not only computers getting large, but having methodology to do it in a better way through Lagrangian microphysics.
I'm confused, so we'll have to talk later. But just a quick comment. I think DNS of this type is closer than you think with the use of GPUs. I remember the talk I gave a couple months ago that one GPU is equivalent to roughly 100 CPUs. So it's like a sea change in computing power.
Can you do a simulation? Well, remember, DNS has periodic domain.
No, it doesn't have to. You can do DNS of a cloud.
That doesn't have to. Yes, I agree. You can do periodic on perturbations, yes, and bring mean profiles. That's possible. But you cannot do a cloud like that with real DNS, maybe scaled-up DNS with 1 meter grid lengths. But DNS spectral codes are not ready to bring mean profiles. I don't think so, unless they work on perturbations. I think we're talking about different things. We can talk.
I'll maybe have a quick comment, too, about the why use DNS still. So we, in particular, work that Kamal is leading is using DNS to basically inform the subgrid scale parameterizations that go in the LES. So yeah, that's the key, I think, linkage. Let's do one more with Andy, and then Andy Prine, and then Andy Heimsfield as a follow-up to his question, and then we'll call it.
So this might be a silly question. I've never used DNS simulations before. Do they have to be a cube, or could you just have more column domain? Because it sounds like the horizontal boundaries are not the issue, it's the vertical extent.
And in fact, I coded something like that. Yes, you can have, I mean, there's, the way the DNS with periodic domain and same size is driven. I mean, I use finite difference, so I invented a methodology to drive it. It's probably easier or more natural if the box is the same, because you kind of drive your turbulent kinetic energy. But you can have it extended. In fact, I kind of trying to do something like that. And Terry Clark and Bill Hall, if you know people that I'm talking about, did something like that in late 80s, looking at actually an elastic model with turbulence driven in a specific way, looking at activation and growth above the cloud base. But it's a different microphysics. So.
All right, so as a follow-up, Andy Heimsfield said, in Ice-T in the Caribbean, we stepped up from below cloud base in 100-meter steps through the cloud, and he's talking about the aircraft observations. A wonderful data set to look at the questions you're addressing. So more of a comment, I guess.
Well, except that you don't follow individual droplets. You're still looking at, if they have FSSP, it's still maybe 10 hertz data. I mean, individual droplets, you're looking at the cloud through a straw of maybe a couple millimeters across. So all those problems. And of course, we get holography. Well, holography, you're looking through a cloud on a teacup and the stick up is here, and then it's whatever, a couple hundred meters away, because the time that the probe operates, not to mention how long you have to process the data with this three-dimensional distribution. So,
And I'll maybe quick add to that we are comparing the observed DSDs from the CAMP2X observations, and the simulations here look quite good, actually, with that comparison. So that's a little bit of a reality check, I guess, with this particular simulation. So let's thank the speaker once more, and then we can move outside, more discussion.